so.
Well, it's an honor, but most of it, it's a pleasure to be here to celebrate my young friends. And, so, in fact, I'm really happy to be here. I'm often here, as you all know, because I always enjoyed very much both the high quality of these universities which are together today, at the same time as the unusual friendship, the relaxed friendship that exists here, and it's always a pleasure. When I come here, I just feel home, or maybe better. Okay. So, this talk is about an attempt of understanding basic symmetry that may hide in any theory of gravity or extension of it, and in particular in supergravity and in the M-theory project. The ultimate idea would be possibly to find in the algebraic structure of this symmetry a possible way to get out of the difficulties in which the present approach to what's called the M-theory project has. But of course this is not as far as that. For the moment we're going to try just to see that these conjectured very high symmetries like E10, E11 that were conjectured to exist in beyond the supergravity, that we're going to use this, and we're going to use the algebraic structure to construct solutions of supergravity, and the way the solutions are constructed will give us also a hint of what is the meaning of these symmetries. And this is inspired by, of course, all the people who have, and I listed some of them, who are responsible for having suggested these symmetries. And it is a pleasant surprise that some of the results we find are in line with results that one of our guests of honor has found some 10 years ago. So, I'm going to organize the talk the following way. First, I will, of course, review what one means by E10 and E11 and how, in a kind of, for the moment, let's say, very phenomenological way, try to define what are the fields that in space-time one could take out of this algebra. And then we shall use the algebraic structure to construct, after having recalled what are the basic BPS solution of 11-dimensional supergravity that everybody knows, the 2-brane, the 5-brane, Kaluza-Klein wave, Kaluza-Klein monopole. How out of this we're going to build an infinite multiplet of solutions of 11-dimensional supergravity and show that these solutions indeed form in the language of string theory and in the M-theory project, I use that word generally, how they are forming a infinite U-duality multiplet. And then I will make some comment of what I believe is an interest, not only in finding these solutions, but what is the interest that goes beyond it. So, well, before trying to see what are the fields that can exist in space-time, which are related to E10 and E11, let's first review, for many of you this is well-known things, but it might be useful to review it. What are these large groups and how you get them? First, let's consider a simple Lie group. In the usual Cartan representation, these are described by two types of generators. The commuting generators would form the Cartan subalgebra, and the positive and negative step operator associated with positive and negative roots. And positive roots are obtained in terms of the so-called simple roots as a linear combination in the rank space of the group having integer positive coefficients. And I will also always, well, I will in fact in what follows focus also the attention on a special subgroup of the group G, which is the Borel subgroup, which is formed of the Cartan generators and the positive step operators associated with the positive roots. Now, this is the most common way of presenting group theories of Lie group and of simple group. There is an alternate one, is slightly different, which is useful to get a generalization to the so-called generalized Kac-Moody symmetries or Lie algebras. This is the Chevalier-Serre presentation. Essentially it's the same thing, but you focus your attention on the simple roots and you redefine the Cartan generator by taking linear combination in such a way that the simple roots, which are here little e and little f's for the negative one, such a way that the commutator of the simple e and b have a very simple commutation relation, so they get back e to the alpha. Having the simple roots in this way, this change of this specific linear combination makes that the simple roots are now eigenvalues with are now in fact connected to the Cartan subalgebra or the Chevalier generator by some matrix, which is a Cartan matrix, in terms of which the whole group structure is defined. Namely, in order to get all the group structure, you take all the commutator of the simple roots of these simple generator, and you find that the Serre relation tells us that if you take a given generator, positive here, and commute it through another one, a given number of times, you end up to 0 in a way which is related to the Cartan generator. So the existence of the Serre relation makes that when you have these simple Lie groups that we all know and which have been classified, the Serre relations are responsible for the fact that the algebra is finite, because after a while the commutator don't give 0 and you don't get any new commutator, any new generator. So the Cartan matrix essentially defines fully the group, and here is an example, the Cartan matrix of V8. You see that it has 2 in the diagonal, it has -1, and in general it has to have minus negative integers for this relation here to make sense in non-diagonal thing, and that can be represented by here a set of nodes corresponding to simple roots and some links here which corresponds to the -1, which are here, which are the off-diagonal elements of the Cartan matrix. Now, once you have done this, you can generalize this in a very simple way. For instance, suppose that for some, for the moment not necessarily good reason, you would add 3 nodes to the linking diagram here, that's the name of this, of course, which is just a representation of the Cartan matrix. You just add here 3 nodes. And you keep the same general formulation of what you call a Lie algebra. The only thing that happens is that because you have added these 3 nodes, the Serre relations are not enough to close the whole thing on a finite number of generators, and the algebra becomes infinite. So that is a simple example of what's called the generalized Kac-Moody algebra, and this is the E10, which we'll see, E11, which we'll see before. The reason why these are labeled from 1 to 11, well, It's because here I will play more on this than on this, so I call this one, label this one from 4 to 11, so I can call this one from 1 to 11. That's it. Right, so we get to the next one. Now, why do I give these examples? This is not, of course, just for fun. Well, it is for fun, of course, but it's something that naturally comes when you study, for instance, supergravity, or in fact gravity in general. So I wrote here the bosonic action of 11-dimensional supergravity, and with a Chern-Simon term here, and this 4 form here, which is typical of now let's suppose you reduce this to 3 dimensions. You dimensionally reduce this theory to 3 dimensions. Why 3? Well, 3 is an interesting number because then all the vectors that comes in the dimensional reduction can be dualized to scalar, and so essentially, except for gravity, you only have scalars. And you expect these scalars to be invariant under some group. Which group? The first thing that comes in mind is just because you make a dimensional reduction, which is equivalent to a compactification of an infinitesimal torus, that you will have just a linear group of the deformation of the torus, because the massive mode has been taken out. So you expect the group to be GL8. Actually, the group is larger because of some accidental degeneracy in this world due to the very special structure of this 11-dimensional action, having to do with the dimension, having to do with this thing, and having to do with a particular form of the Chern-Simon. All of that, of course, is not accidental, but from the point of view of just group theory, you can say this is accidental, and you transform the group into a group of the same rank, but which is now a simple group, which is E8, and in fact a non-compact form of E8. Now, the scalars should be invariant under E8, but they are in fact invariant in a nonlinear representation of it, namely in a coset, which is the coset space of E8 divided by its maximal compact subgroup SO16. And the E8, which I consider here, of course, is a non-compact form of E8 because it starts from here, but SO8 is its maximal compact subgroup. Now, the nodes here labeled from 4 to 11 have some meaning. They are related in not a completely direct way, but to visualize what they mean, you can see that these nodes, which correspond to the simple roots, correspond just to the non-diagonal metric element for neighboring indices, and this special root here, which was responsible for this accidental degeneracy, is not surprisingly related to the 3-form potentials of the 11-dimensional supergravity. Now, let's suppose that we decide we go to make a dimensional reduction to 0 dimension. Strictly speaking, it's not true. It's not a reduction to 0 dimension, but just suppose you don't think too much and you want to do that. What you would say is that, after all, you have already taken care of all the effect of this accidental degeneracy here, and you just extend these line, which has to do with the metric of the torus, which essentially call this the gravity line, by 3 nodes. And then you say, this is symmetry. Maybe that symmetry, that is where, of course, for the moment you have no reason to believe that that's true or not, but maybe that symmetry plays an important role in the just because, after all, it is one of the solutions. And we can discuss later, there are other examples in which a dimensional reduction to 0 dimension or to 1 dimension plays an important role. So, so let's suppose we do that. And we say, okay, this is the basic symmetry. Now from there we are going to deduce everything. Of course, we have to do that step by step. And the first thing that we're going to do is to see if we can a little bit understand the phenomenology of this. In other words, can we understand some space-time fields which would be related to this group structure or this algebra structure of E11. And that we shall do. The first thing, of course, is to emphasize that this line here with red labels is related clearly to gravity, and therefore we consider a level decomposition of the regular representation of E11, which is all this generator, in terms of irreducible representation of A10, which is just up to the scale factor GN11, so it's SL11, and they are given by irreducible tensors, which can be characterized also by a level L, which is a number of times this special root comes in, this special generator comes in the irreducible representation. So, what type of fields would you get there? Well, clearly, if you take L equals 0, that means this red line, you just get the regular representation of A10, which are just these given here by these commutation relations, which in addition you have to put the trace to be 0, but that's what you get at L equal to 0. At L equal 1, the Young tableau tells you that you have, not surprisingly, an anti-symmetric tensor in 3 indices, because we knew that in 8 dimensions this was just the field A9, 10, 11. And so we have a field at L equal, which is an anti-symmetric tensor in 3 indices. And higher, we have a more complicated Young tableau, and I represent every higher positive level by upper indices and and negative level by lower indices. And but these, though, we can say, okay, these are generators. In the group or in the algebra, they would be parameterized by fields, but this phenomenologically, we immediately will encounter that these are too many fields, because we know already from the reduction to 3 dimension that only the coset space label physical fields. So we should do something similar here. So let's do that. By the way, if this would be strictly a reduction to 0 dimension, this would be fields which would depend, let's say, at most on one space-time point. But I shall leave that point open. I shall not make that assumption, but only that the tensor structure is correct. And then let's try to do something like constructing a coset in analogy to what happens in 3 dimension, in the reduction to 3 dimension. Now, so taking out the maximal invariant subgroup can be done by selecting the so-called Chevalier or Cartan involution, which puts every Cartan generator, which can be taken to be the K with the same indices, into minus itself, and every positive roots into minus the negative counterpart. Every positive generator into negative counterpart. But here, because we have a time in the problem, we want to take that into account, and we take a more general involution, which is that we multiply these things by some epsilons, which are +1, if the label here is supposed to label a space indices, and -1 if it's a time indices. Now, we can now define the subalgebra in analogy, or slightly generalization, of course, of what has been done in 3 dimension, saying that call K11 minus, the minus is for this temporal involution taking this minus sign in, take K minus as a subalgebra, invert the evolution, and then we are left with a coset E11 over K11 minus. So we would now say, well, maybe this is the group, or this is the structure, in analogy with Eden, in which the fields that the parameter of this coset would be the physical field, and not all the one we have done by the tensor reduction of the first thing. But this is still a lot, and we are going to consider a subalgebra of E11, which is E10, and in which we just separate in a regular embedding the first node here, and I have just written here for further information the Chevalier form of the Cartan generator, the commuting one, which now go only for 2 to 10 and for 2 to 10 for the gravity line, And the last one, related to the special one, called H11, is given by that expression. As you can compute, it's not very difficult. And now the subalgebra K11 contains now two subalgebras in E10, one which corresponds to K10 plus, which is in fact the fact that the temporal involution has induced in E10 just a usual Chevalier involution if the time was in 1, because there's no indication of the time anymore. But we could make a Weyl transformation in E11 and put the time somewhere else. And if we put the time somewhere else, then we have again a temporal involution here, and we have a new coset space, which is E10 over K10 minus, meaning that here also we have kept a Lorentzian signature. Now, once we have this, we can now go further and now ask, can we define fields as parameter of the coset space, let's say E10 over K10 minus. Just I want to say here that E10 over K10 plus has been used by many people for cosmological type of structure. This is how one gets the well-known cosmological billiard. But for what we are interested here, only for most of the talk, which is static solution, it seems much better to go to the temporal correspondence, which is E10 over K10 minus. Why not go to E11? Well, in a sense, this contains a huge gauge type of structure in addition, and we want to simplify life. So, but we go to E10, but we'll see that we go to E10 in a very specific embedding of E10 in E11, which is the regular embedding. So, well, we want to parameterize the coset E10 over K10 minus. So one way to do that is to go to the Borel subgroup, because this forms a representative of each class of the coset. And I've written here the representative, which is of course infinite, where there is a level 0, which has been written separately here, which corresponds to the A10 essentially, and the positive level here, where every index now goes from 2 to 11, because the index 1 has been dropped. We are in E10 and not in E11. Now, what's the meaning of these things? We know that these ones with these deformation of the torus in the simple reduction has to do with gravity, and it's not difficult by many arguments to show that these are related to the Wheelbein by the exponential. And so these are the Wheelbein out of which we can construct the metric, so the level 0 is related to the metric. There is a slight problem, of course, that the index now goes only from 2 to 11, but with the embedding of E10 in E11, we have an embedding relation, and that fixes the last parameter here in terms of all the other, in other words, specifying the gauge we are using in gravity. And these are the relations that you can prove come from the embedding of E10 in E11. When this is done, these relations can now be taken in 11 dimension, and therefore the level 0 can be identified, at least as far as the indices are concerned, to the metric of gravity. The level 1, we have a 3-form potential, so that we suppose that this is related to the form of the supergravity form. The level 2 contains a 6-form potential, which is naturally, and checked by what you do in 3 dimension, naturally identified to the Hodge dual of the 4 potential. In level 3, well, you have a mixed thing with 8 antisymmetric indices and 2 symmetric ones. When all these indices are not different, 2 of them, let's say, be equal, then these 8 antisymmetric indices here in E8 would not be there, and this is, again, can be identified by looking at the solution to essentially the graviton in some dual form, which I will explain. What happens after, for level greater than 3, and even for level 3, when these indices are not equal, nobody knows, up to the end of the talk, of course, because these are not related to any classical type of fields. So let's see now what we can do in order to try to understand in this phenomenological way in which we associate space-time fields to the algebra what we can say about these fields. Not very much, but nevertheless something. Well, let's first remember I'm going to focus my attention on BPS states because that's the simplest thing to do. And oops, that's too far. And the simplest one is just the 2-brane and the 5-brane in 11-dimensional supergravity, which are given by metric that I've written here. I've put for reason of commodity the time in 9 here, and the potential is given in 1 over h. All of this is given in terms of function h. I will say in a moment what that means. The 5-brane is given by a very similar type of metric with some change of exponentials, and the time, for some reason here, I put it in 3. And now, then everything is expressed in terms of h in this solution of gravity, but h is what? H is a harmonic function in the transverse non-compact dimension for these branes, and we can in fact average the branes over some dimension if we compactify them, and then it's a harmonic function in the remaining non-compact dimension. This is the solution of gravity. Can we transcript this into the fields that we have just defined? Yes, because these take only those, only make use of these classical fields up to level 3 that I made. The M2 is given by HH, which from the relation I previously showed here are related to the metric. So I can write here the metric of M2 in this form, and 8 with the time in 9 is just given by 1 over h, as here, and M5 here is given by that. There's also the Kaluza-Klein wave, the Kaluza-Klein monopole. Here is the diagonal metric which comes out. I haven't written the fields here for the Kaluza-Klein wave. This is a non-diagonal metric which corresponds to adding here some level 0 non-diagonal Wirbine, and for the Kaluza-Klein monopole one can use a dual formalism using the level 3. So these are how they are written in E11. In the addition we have to impose that h is a harmonic function. Now how are we going to use this to construct other solution of gravity? Now here is the trick. The working hypothesis is the following. We're going to start by writing the, let's say, the M2 and the M5 to simplify life, right? In terms of the E10 type of thing. I just forgot to say one thing here. I separated by a line here the index 1 for H11 because this is not a property of E10 but of the embedding of E10 in E11. Right? Because in E10 we have only from 2 to 11 and from 1 to 11. So here now, I just rewrite, it's just, I'm not going to say, just checking that all these numbers that we get just build up here the generator H11 in the Chevalier representation of the special Cartan thing. Special Cartan generator, and here is how we write the M2, and here we write the M5 in terms of a function h, and I'm going to stick to 2 dimensions for the rest of the 2 non-compact dimensions for the rest of this talk. And now, if this is so, the only thing that we're missing here to reconstruct from this gravity is the fact that we have to know that h is a harmonic function. Here I made the fundamental assumption, which is the following, that we use the huge duality, the Hodge duality, which is here, and when you put the metric that you have from here inside here, you find that these reduce to these relations, which are just a Cauchy-Riemann relation for the complex function h plus ib, therefore H and B are harmonic functions. Therefore, the assumption will be that instead of this set of state, we can take the dual one, which are here, and so we have here the new prime and the new second, which are equivalent to new one. These are just definition of what M2 and M5 can be represented, how they can be represented in E10. Now, what we now do, the basic things that we do, is the following. By Weyl transformation in E9, we can always reach any positive roots, which is therefore a member of the Borel representative of the coset space we want. And therefore, we are going to say, okay, let's take the Borel representative of any positive roots of E9. We get it by a Weyl transformation. This one is essentially not changed. AL, which is the field, multiplying the generator RL, where L is some set of variables in E9. And this can be computed by just straightforward Weyl transformation. Now, this of course has nothing to do apparently with 11-dimensional supergravity. But we're going to see that using duality, the way I explain it in the lowest case, of the M2 and the M5, and using compensation that will be defined in a second, we shall be able to represent this Borel representative in an equivalent one which contains only the tree form and metric, and therefore we shall see and check that these are solutions of 11-dimensional supergravity. In this way, we shall find an infinite number of solutions of 11-dimensional supergravity, and we shall also find that because they are obtained by Weyl transformation of E9, something this man knows very well, they are related by U-dualities to the M2 and the M5. Now let's do this. The first thing is to select some kind. Okay. The first thing is that we're going to collect a simple subalgebra of E9, which is a subspace of E10, and we're going to take this, and the simplest thing is to take the commutator of these generators which we had, which we're defining essentially the 2-brane and the 5-brane, and we generate this way a group. This group is very easy to identify to the affine group of SL2 with central charge, and this is where, in fact, while we are sticking, as we shall see, to the simple roots of E9, to the real roots of E9, this term here, which is plays the role of a central charge, is in E10. And so the fact that we are in a regular representation, in a regular embedding of E9 in E10 and E11 is used in a deep way. And so we have this, and this now makes an infinite set of generators of these group A1 plus, which is a subset of, which is a subalgebra of E9 in this embedding in E10. And here are the generators with these specific numbers which we took here. And there are 3 towers essentially. A tower 3 which contains one more 3-index object than a 6-index object, a 6 tower which contains one 6 object more than a 3 one, and the other one which contains as many 3 and 6. Now, these two here, now there are no other ones. That's a consequence again of the Serre relation. So this is the full algebra. Now these ones are all real roots. So we should find solution for all these real roots. We should find solution for all of these. These are null roots in the sense that that the scalar product of itself is 0 and not a positive number. And this we are not considering here for the moment. So the project is to find all the roots which are here, which are roots of A1 plus, which are also roots of A9, E9, and associate solutions, BPS solutions to them. Now, as I said, we are going to reach all the roots of E9 by Weil transformation. So this is the Weil group of this subgroup A1 plus. You see, we start here with R13, which is the root corresponding to the 2 brane, or the dual of the 5 brane, and R26, which corresponds to the 5 brane, or the dual of the 2 brane. Now, here we see that with 2 Weil transformation, namely the one that's perpendicular to the, well, that makes a reflection in the hyperplane perpendicular to alpha 11, is one of them, and the other is minus alpha 11 plus delta, where delta is precisely the null root which defines the lowest term of this imaginary or null tower that we had before, and which has the property, of course, of being a null root, and that commuting in all the, and having a zero scalar product, with all the roots which start with 3, which are those which in fact belong to E9 and not to E10. And so with these two, you see you start with, let's say, R3. You have, and doing successive Weil transformation, you both flip between the 3 tower and the 6 tower, but at the same time you only get half of the right of all the positive roots and or of the real roots, let's say, of this subgroup, but you can start with this one, R2, and do the same thing, and then you get all of them. So we have essentially 2 sequences, which I'll call the M2 sequence, the one with the blue line, and the M5 sequence, the one with the dot F5 lines. And these 2 sequences of Weil transformation generates all the real roots of the subalgebra A1 plus SL, the affine group of SL2 in E9. So we do this, and let's see now how this goes. Let's start with the first generator in the M2 sequence, and which was, in fact, the one which went from R1 to R5-6. So we go to the level 1 to the level 5 with this transformation, and here is what we do. So first we compute the Borel representative from that Weil transformation, and we get here the Borel representative, and this is the computation we get. Nothing happens for the R5 here, it's still 1 over 8. Here the Cartan, which was previously plus H11, has become minus H11, minus 2K22. It's a small computation, but it can be done very easily. Now, and H is what we had before. So now, we're going to say that we want to add this assumption that we use the dual to be equivalent to this one. So what's the dual of nu 5? This is by definition the one which is obtained by the same Weil reflection as the one leading from R1 to R5, the lower index being the level, right, of E10. So we do this, and we compute this, and we get this number. Nothing is changed in the Cartan, but here the 1 over h goes to, in fact, minus b. Why minus b? That you have to compute, and you see that the sign is fixed by the Weil transformation. And then you now use the fact that minus h1 minus k22 r minus 2 and r2 is a subalgebra SL2. To write this in matrix form, where the k22 remaining k22 commutes with this and is therefore a unit matrix, so this can be written in matrix form that way. And you see what's happening is, this is the dramatic thing that happens, that we have here an r minus 2. In other words, we are going to a negative root. Having gone to a negative root, we are no more in the Borel representative, so we can't use our great scheme. But we can, because there always exists, that from the Zawad Iwasawa theorem, we can always find a representation of the compact subgroup of this, which brings back this to the original Borel representative, and therefore we multiply this by a SO2 matrix, which is here, and a little bit of computation shows that you can put here this one, this B, which was here a negative root, and therefore in the matrix representation was in that corner, to a positive root. So this is the compensation which puts this negative root into a positive root. By the way, it is not an accident that we get a negative root here. The point is that it is very easy to prove that the sum of the levels here by the y reflection of A1 is always conserved and equal to +3. Therefore, once you get to a higher level here, the only way to get +3 is to get negative numbers. So it's built in the cards that you are going to get negative roots and therefore going out of the Borel subgroup. And then you bring it back and you get this. So here you have the expression now of the Borel representative at level 5 in terms of the dual one, but now you can use the ordinary Hodge duality to take it back to the three-body potential using the metric that you just found, and it works. What you get is you get this form when you do the Hodge dual for the R13. Now, what have we realized here? What we have realized is the following thing. We have started with the M2, which was here given in terms of the metric and the tree form, and that's a solution of Einstein's equation that we know. And this is a harmonic function coming from the fact that the Hodge dual of H is just B, and this is a harmonic function. Now we go to level 5. We found, after having done the duality equivalence and the compensation necessary to go back to the first Borel subgroup, we find that metric. That metric, except for that factor, has the same form as that metric, but with another function, H tilde, which is that one. But using again the Hodge duality, we see that this is equal, that the Hodge dual is this one, and again we see that there is a complex number H tilde plus IB, which is just 1 over H1 and therefore is also analytic. And therefore H tilde and B tilde are also harmonic functions. And therefore these are harmonic functions. Were it not for that form, they would be automatically a solution of Einstein's equation. Now that form here is precisely of the form of epsilon 1 bar, which is a modular. And because it's a modular, by a conformal diffeomorphism, you can always rewrite it back in terms of eliminate that factor by diffeomorphism. But because this is a conformal diffeomorphism, it maps harmonic function into harmonic function, and therefore this is a solution of Einstein's equation again. So we have proven that. Because the fact that the solution of Einstein's equation only requires that it's a harmonic function, and of course in physics, in particular for the M2, you have to fix the particular singularity which tells you that it's M2 element pathway. That will come back. Now this is called the Earth's potential according to knowledge of other people, and so we have now found a solution 5. Now, once we have done this, it's easy. Modulo some type of certility, which I'm not going to enter in because it's a limited time and I don't want to kill everybody, including myself. So now we're going to do the same thing over and over again. And it's not difficult, in principle. Oops, that's too fast. Here, we have gone from R1 to R5. We can go to any higher things here. Do a duality, which brings back a negative level. Make a compensation. Do a sequence of these duality and compensation up to the moment that you reach a tree form. And therefore you can do it everywhere. In addition, you don't need to do all of this because you can do it recurrently, because two horizontal lines are related by the same Weyl transformation. So you just follow the right set of things. At any level, you have just to do one duality and one compensation. That can be done analytically very easily, and therefore you can get the analytic solution for all the A13 level that you have, starting for the M2 sequence. Now, this is coming from, it's a generalization of the M2 brane. Now you can generalize the M5 brane. The same thing. I'm not going into detail. And now you can do everything else. You can go on. And you do the same thing for the wave sequence and for the Kaluza-Klein monopole, which in fact are again Weyl transform of the M2 sequence and the M5 sequence. So by Weyl transformation you can avoid a lot of work. You just see that these new Weyl transformation are these new objects, and I don't go into detail, but you can just work them out, and you again get an analytic thing. There's a slight subtlety here which I want to mention anyway, that here the level of the KK wave and the KK monopole involve in fact a duplication, because at a given level, that the level is the number of H alpha 11 that comes into the E10 decomposition, you have a doubling here, one belonging to the two belonging here, either to the Kaluza-Klein wave or to the Kaluza-Klein monopole. But that is a redundancy, as we can prove, because it just corresponds to a change of coordinates, a switch of coordinate 3 and 9, let's say, or something like that. So, in fact, you go all of them for a fixed set of indices, then you perform the Weyl transformation that changes the indices of E9 between itself, and then you get all the roots of E9, or more properly, all positive roots of E9. To each positive root of E9, you get a BPS solution. What I want to emphasize is that this has been done essentially purely algebraically. From the E9 algebraic structure, when it's embedded in E10 in order to fix the K2, and when E10 is embedded in E11 in order to fix the first coordinate in terms of the order. And this is the result. Now, what does it mean? Well, because all these representative are equivalent, I might as well have stick to the first one, which to begin with we didn't know to have anything to do with 11-dimensional supergravity, but now we know, because we have constructed by equivalence in the way I define solution for each of them of 11-dimensional supergravity. But if we don't do all this thing and keep the field that we encounter in the parameterization of the coset space of E9, which are those EL, then we know very easily what's coming out. The EL is still of the form 1 over H, and these is very easily computed out of the Weyl transformation. And in addition, one can find that this again defines a metric. It is no more 11-dimensional supergravity, but it's a metric which we can call an effective action, which has a matter field due to this, and this action has its minimum as a solution of the metric that we obtain here. So there is essentially for each solution a dual solution in terms of an effective action, which is written here. Now, the F here has a lower and an upper indices, which means that the Fi is the derivative of this potential, which is here, for instance, for the 3 tau, not at level 1, which was the level at which you have the N2, but at the level 1 plus 3n, which is all the level you generate with these successive Weyl reflections. And it has the following form. If we start with A1 to be A9, 10, 11, having 2 brane in 10, 11, and the time in 9, then we have an addition. For each n, we have a set of indices 3, 4, 11 to the power n, where n is the place in the tau. That's very easy to show. And now, we can now compute the g's which are necessary to raise these indices here, and which will come to a moment here. And these are of this form. They have the G9, G10, G11, where these are nothing else as the one that you had for the M2 branes, because the only change that you get from these Weyl transformation is the G11 and the G22, which is here. So you get, for any member of the tree tower, you get G9, G310 plus these G's here to a power n. These are the ones that you need to raise these indices here. Now, why is this interesting? Well, for a few reasons. The first one is just simply that we can now compute the equation of motion of this thing from the dual Lagrangian by writing the equation of motion here. The epsilon plus and minus 1, I don't go into that. And now what happens is very amusing. All these things here, just looking at the M2 and the 5 matrix, this is always equal to 1. So only this happens, and this G11. G, from the embedding of E10 in the 11, the determinant here for these metric, which is a diagonal, is the product of all the G's. Because this multiplied to 1 is just the product of G11 and G22. But the embedding of E10 in 11 tells us that they are the same. So the square root of G and all these G here boil down to 1, except for these 3 factors here, these 5 factors here, and these factors which are here. And these factors can be easily computed, and it's always h squared, and therefore when you compare to the relative of h, which is 1 over h, you just get the Laplace equation for h, which we know is a harmonic function, except for the singularities. So this is 0, except that because you have taken for h the solution of the 2 branes, there was a singularity, a well-defined singularity, and that singularity is found again in all the E9 structure, as you would expect if this is a multiplet of some U-duality things. But what about the masses? Well, to get the masses, we use a well-known fact that the Weyl reflection on the special root 11 is equal, I think Tom is one of the first who did this in detail, is the same as a double T duality plus reflection, or plus interchange of indices when you interpret it in type 2a, and then you uplift it again. And this is what it means in terms of the usual dualities. So I write here in blue the transformation that the T dualities do in type 2a, and these are the uplifting relation between so-called M theory and 2a. So now, as an example, the M5 here, let me see where I am. Oh, it's okay. The M5, which is here, you see, when we start with the M5, it's the simplest case, but we can do it in general. When we start with the M5, then you see here, no, it's not here. When you start with the M5, the first one that you get here is here. You get to the level 4 by a reflection which is on this special root. So this is the simplest case to see, so I just look at that one for the moment, just as an example. Hey, it's being too fast. Messed up with this machine. Yeah, there's a way to get directly to it, but that's what I haven't yet studied how it works. We try not to go too far. Okay, so we were looking at the mass. So here we have the charges, and now here we have the mass. And so the example is the M5. We know that by this pi reflection we go to the level 4. So according to this as an interpretation of this in U-duality language, then we first go to type 2a where this M5 is N5. Remember we put, the time was in 3, we put the M5 in these direct 4, 5, 6, 7, 8. Then we make a duality in 10 that gives us a KK wave, a KK monopole with 5 longitudinal directions. And then we do a second one in 9 and we get a level 4 when we have uplifted it to 11. So first we start with the M5, this is the mass, then we do this mass, then we go to the NS5, which is given here, then we do these two dualities here, in string theory we uplift, and that's the result we get for level 4. And we can do that for all levels. It's not very complicated. Well, the amusing thing is that defining an action, which is the mass times the radius of compactification, which we can possibly sometimes put to infinity for the time, you get that we have seen all these fields have that form, and they have similar form on the other term. And the general result that you get from playing this to all levels is that you just copy these indices here in terms, this is the recipe, you copy these indices and you write radiuses for them, and then you divide by the Planck length to the required power, and this is the answer for all the E9 masses that you get, or E9 action. At the next page we find the result of the guest of honors and all these things, which is here. If you put all the result from level 1 to 6, and where the time we have put are these, then we see here that the masses, as I say, you just copy them, and if you look at the results which were done 10 years ago by these people, they are identically the same. And in fact, what we now know is that up to level C3 we had the usual BPS, now we have the unusual one if we go up to level 6, which have now all 8 longitudinal space dimensions. If we go to higher level than 6, we find that the miracle that happened at level 6 here, that the time curvature was linear, and therefore you could decompactify the time. That cannot be done here, and therefore here, for all these other solutions, there are only 2 non-compact dimensions, which are the Euclidean dimension 1 and 2, and the time is compact. So that is the result you get, and now I am at my last stage, and I want to say, to summarize what we have. So we find an infinite set of BPS solution of 11 dimension supergravity, and these are an infinite multiplet of U-duality, which is generated by the E9 Weyl transformation, where E9, I repeat, is embedded in E10 in a regular way, and E10 in E11 also in a regular way. They can be also interpreted in a dual form, which is nice to see the mass structure and maybe essential to understand the charge of these things, where charge has to be taken with a quotation mark. But these transcend 11-dimensional supergravity. Why? Well, in a sense, all what we have done for these E9 type of things, we have shown that they reduce to 11-dimensional gravity solutions. But these are for the roots which are in E9 and in E10 and E11, but they are in E9. Now there are roots which are not in E9, but only in E10, for instance, and those cannot be reduced to 11-dimensional supergravity. We can give an example if you wish later, but not now. I am at the end of this cinema. And so this contains more from which you would guess that at the E9 level you have not introduced with these algebra new degrees of freedom, but essentially something more tricky. But if you go further than that, then you really have introduced new degrees of freedom into the theory. And finally, I want to say that despite the fact that we are doing BPS state, what we have obtained is something which has significance much more beyond BPS state, which is the following. I give an example. Let's suppose that I have done 1, 2, 3, 4 while reflection to arrive here. Then I make, what was the way to obtain a solution? I took a duality which goes from R13 to R minus 10, because this is, the sum has to be 3. Then I make a compensation, goes to R3, and I have gone down on the 3 level by 1 unit. So in fact, the number of units, if and then I can go on, and if I go down 4 units, I go back to here. Now the only reason why the solution here is not the same as the original one is because there was a compensation. In other words, because I have hit a negative root and had to compensate. If I would put by hand all the compensation equal to 0, I just have Hodge duality. So what we have here is a generalization of Hodge duality by an infinite set of non-closing duality whose structure has been explicitly done in the case of BPS, and although we do not have an analytic form to do it more generally, its very definition is quite general, and therefore it is that way, I think, that in the Kac-Moody algebra formulation that one is trying to do, that the non-linearity of gravity, which makes that things are not as simple as you would like it to be sometimes, that this is encoded in the fact that there are non-closing dualities and infinite dualities that we have put into evidence with this little exercise. Thank you.
Questions, comments?
If I understand correctly, we begin with a solution.
I'm not as young as these people here, so my ear is bad.
Gravity corresponding to a root with a given length, and then you apply by reflection to it to find the solution.
Excuse me?
Okay, so you begin with a solution to supergravity.
Yes.
Corresponding to a certain root.
Yes.
With a given length.
Are not included in these via things. I would expect that they would correspond to piling up of these things, but I am not. Yeah, I come back. But, I'm sorry, but my ear is deteriorating. That will happen to the jugularies in some 20 years like this. But you have already. Okay. Yeah.
What is precisely the relation? You relate every bosonic field to a Cartan generator and every BPS solution to a root. And so is this the relation? And what about other physical states, non-BPS states?
No. For the moment, this is, of course, not a general identification of what all these fields mean. For the BPS states, the fields which are there, well, I should not say for the BPS state, all the roots of E9 seem, for BPS states at least, to have a well-defined interpretation through these non-closing dualities in terms of the treeform. For non-BPS state, we expect the non-closing duality to remain valid, and therefore these roots are still related by non-closing dualities to the basic root. So they are not defining, in my opinion, they are not, I don't know what Herman think about it, but I think that they do not correspond to any new degree of freedom to the system, but rather to the structure of the space-time interpretation as general relativity. That, I think, is what it means. Once you go beyond the, well, there are three things. Once you go for real roots beyond the E9, then I think you hit solution which you do not have, cannot be expressed as solution of 11-dimensional supergravity. That can be shown in some example, and therefore I would expect that these two correspond to new degrees of freedom which transcend 11-dimensional supergravity. In addition to that, of course, there are also other rules which are imaginary or more general, and what these correspond to at this level, my knowledge is not known. And we do not have a well-defined indication of what they mean. But it's quite clear that this type of algebra, if it does work, indicates that there is something which is more general than 11-dimensional supergravity as being simply a low-energy approximation to M theory or whatever. I also want to emphasize that because everybody likes M theory and well, I don't, but it doesn't matter. Then it's related to 11-dimensional supergravity. I did this in the context of 11-dimensional supergravity. But I think what really is beyond it is that it's a property of gravity that we are studying, and that it might very well be that all of this, once the glamour of supersymmetry may fade away, perhaps, or something like that, that there will still be something which will be left out.
Okay, well, I think we should thank